In this video, we are going to assess for interaction effects among independent variables in logistic regression analysis using Stata. In our previous episodes, we've checked for the assumptions and we've selected variables to include in the analysis. And in our subsequent episodes, we shall be demonstrating how to carry out step 4 up to 6. Consider liking and subscribing to the channel so that you don't miss out any of our episodes. But what is interaction? Interaction simply means that the effect of one independent variable on the outcome depends on the level of another predictor variable, meaning that predictors or the independent variables modify each other's effect on the outcome. In logistic regression, interaction is checked using the chunk test, also known as the likelihood ratio test, which simply compares the reduced model, that is the model without interaction terms, versus the full model, that's the model with interaction terms. This test compares the negative 2 log likelihood values that are produced for each of these models to see whether there is a statistically significant difference. So from this, we have got two terms, the reduced model and the full model, meaning the full model is the one with interaction terms. So we are going to form interaction terms among our variables. Interaction terms are simply product terms of the two variables. For example, if we are forming an interaction term between age and BMI, it is simply generating a new variable that multiplies the values of age times BMI. Same thing for age, gender, age, smoking status. We can go ahead and get all the possible interaction terms from this data set having 4 variables, and we would have 6 interaction terms. Looking at our hypothetical data set here, which has our outcome hypertension, which is binary, 0 for no hypertension and 1 for hypertension, and about 7 independent variables that we want to use to predict hypertension. Some of them are numeric, like age, BMI, and cholesterol, whereas some are categorical, such as sex. We have smoking, physical activity, and family history, coded as 0 and 1. One would ask themselves, how many interaction terms would I form when I have these 7 independent variables? Sometimes we even have 20 or 30 or more variables, which would mean very many interaction terms. To determine the actual number of interaction terms that you should form for your full model, there are some questions that we have to ask ourselves. One of them is, do you have a main exposure in your study? By main exposure, let me give an example. If your research question is, what are the factors associated with hypertension? It means that you do not have that one particular independent variable that you're paying special attention to. All the independent variables are considered as potential predictors. There is no main exposure there. Compared to if your research question was, is age associated with hypertension? Yes, you have other variables, but your main focus is age. So age becomes a main exposure. So we are starting with a scenario where you do not have a main exposure. You're just looking at factors associated. So if you have no main exposure, the next thing to ask yourself, what is my sample size? Is my sample size adequate? By adequate, we mean at least 40 cases per variable that you want to include into your model. And here, it is not just about the 4 main variables, for example, age, BMI, gender, smoking status. We are considering these 4 main or basic variables plus the number of interaction terms that you're most likely to form. For example, here I have the 4 basic variables plus 6 possible interaction terms if I'm to form all. That would give me 10 variables. So that would be 10 times 40. I would need at least 400 participants if I'm to run a full model having all the interaction terms plus the basic variables. When I look at my data set here, I have about 150 participants, meaning my sample size would not be enough. So if the sample size is not enough, like we've just seen, still under when we do not have a main exposure, then the option we have is to use stepwise method to obtain only significant variables and form interaction terms among them. Let's go to Stata and see what we mean by this. Now that I've determined that my sample size is not enough for me to create all the possible interaction terms that would be possible, because I would have to create interaction term between age and sex, age, BMI, age, smoking, age, cholesterol, age, physical activity, all through up to family history. Then again, sex with the rest, BMI with the rest, smoking, those would be very many interaction terms. So what I would do is to run logistic regression using a stepwise approach so that I drop the non-significant variables. To run the stepwise, simply go to statistics, go to other, and then you go to stepwise estimation. In this dialog box, we specify the command for the type of the regression we are using. So we are using logistic regression, whose command is logit. So click on it and then specify the independent variable, which is hypertension. It should be binary, coded 0 and 1 for the outcome. Then we add here our independent variables. So we put in one at a time, put age, okay, click OK. Then we put in the next one, which is sex, term 2, click OK. But I feel lazy to use, to include all the independent variables through this approach. But I just wanted to show you where you would get that stepwise command. So click OK. Sorry, you have to specify the significance level. Remember, we are looking for statistically significant variables. So we have to specify at what p-value should a variable be removed from the model. Usually, our alpha value is 0.05. Then click OK. You can see that in this model, we have only included 2 variables, but all we needed is this command, so that besides age and sex, we are able to add the rest of the variables simply here by putting them all, which is very simple. And then click Enter. So what stepwise does is that it starts with a full model and it keeps dropping variables that are non-significant. It shows you that it removed family history first. Its p-value was this, and BMI was removed last. Its p-value was this. So since you do not have adequate sample size, you are only going to form interaction terms between these variables. Interaction terms are simply generating a new variable that multiplies the 2 variables, that's age and sex. So we shall just go to data, create or change data and create a new variable. We are giving a new variable name, age, sex, and then we specify the expression here by clicking create, and we double click on variables. We are having age, double click on it, it will go into the box, and then the multiplication sign here, then the other variable, which is sex, and then click OK. So we are creating a new variable called age sex, the interaction term between these 2 variables. You can give it a name of your choice using this expression, and then we click OK. So I've created the rest of the interaction term between age and cholesterol, then between sex and cholesterol. Those are the 3 interaction terms that we can get from these 3 variables. That is one step of determining the number of interaction terms that you can form. So now that you've formed the interaction terms, let us go and fit the full model that is having the basic variables, and the interaction terms. So to fit the full model, simply go to statistics. We have binary outcomes and logistic regression. The dependent variable here is our hypertension. And our independent variables, we are fitting a full model. We have all the basic variables plus the interaction terms. That is age, sex, age cholesterol, and sex cholesterol. So the full model has all the basic variables and only the interaction terms that were formed based on the criteria that you've used of selecting which variables should I form interaction terms with. Then once you're done, click OK. So this model having the interaction terms is what we call full model. Remember that whatever we are doing is to run a chunker test, which compares a full model and a reduced model. The full model includes the interaction terms. So we've gone through the process of determining how many interaction terms should I form. And we finished that. We've formed the interaction terms. It is time we've run the full model. So we are storing estimates of full model. And to do that, simply go to statistics under post estimation. Then you go to manage estimation results and click on store current estimates in memory. Then click launch. It will ask you for the name of that estimation. So this is the full model. Click OK. It is telling us that it has stored the estimates for full model. It is time now we run the reduced model, which is simply this model here, but without the interaction terms. That's the reduced model. We enter, and still using the same command of estimate. Now we are going to estimate store reduced model, and we enter. So we've run both models. We've kept them somewhere. Now we go and run the chunk test or the likelihood ratio test to compare the models, whether there is interaction or not. To run the chunk test or the likelihood ratio test, simply go to statistics, under post estimation, go to tests, contrasts and comparisons, then go to likelihood ratio test, comparing models. So we have here what we've stored. We have the full model and reduced model. So whatever you put either way, one should be this side, and then the reduced, or whatever you've chosen, the other side. And we check the options for display information about the two models. You can even check for display descriptive information. Then click OK. So this is the chunk test that we are interested in. The null hypothesis is that there is no interaction. And if you have a p-value above 0.05, it shows that we fail to reject the null. There is no interaction. We drop all the interaction terms and proceed without interaction terms. Our variables are not interacting with each other. We also have some additional statistics here that you can interpret, but basically this test here is utilizing the log likelihoods for the null model and the model we've just fit. We have the values for reduced and the full. Stata gives you log likelihood, but it is using -2 log likelihood. It is multiplying these values by a factor of -2 to make them positive. Then we have other criteria for selecting models. We have the ICAC information criteria and the Bayesian information criteria that put into consideration the model fit using the log likelihood values, but also consider the complexity of the model, how many parameters are in the model, so that you avoid overfitting the model. Lower values indicate that the fitted values are similar to the actual values. So a model with lower values is considered a better model. From this, we can see that the reduced value for AIC is 171, which is lower than the full model. So based on AIC, the reduced model without interaction terms is better. Similar thing for the Bayesian information criteria here. It has lower values for the reduced model, which are all in agreement with the p-value that we've just obtained here. So based on this, our reduced model is better than our model with interaction terms. So the interaction terms are not making any improvement in our model. So there is no interaction. We drop them. Then this one here, I always just like running it so that you're sure of which models you have in this test. Sometimes you rerun things and you name things thinking that you've stored the reduced model of the current estimates. Kumbe you've stored the reduced model of a different type of maybe linear regression. So just to confirm what you've run, this was logistic, outcome was hypertension, parameters, and So from this, we do not have interaction. We drop all the interaction terms and we proceed with our reduced model, having only the basic variables for the subsequent steps. The other thing that you need to note is that if you had a main exposure, you would only form interaction terms between the other variables and the main exposure only. For example, if age was our main exposure, then we would form interaction terms between age and the rest of the variables. Then the rest of the steps continue as we have done. If you found this video helpful, consider liking and subscribing to the channel so that you don't miss out any of our episodes. So next we shall assess for confounding in binary logistic regression. See you in the next episode.